So hello everyone. Welcome to our talk, Counter-Strike Global Offsets, our journey into exploiting the source engine. And today we're going to talk about how we pwn CSGO clients with a malicious server. So first off, I wanted to talk a bit about motivation. So Counter-Strike Global Offensive has a huge following and lots of players on Steam every month. Additionally, it also has like a very lively esports community. There's already been successful prior work, which in combination with the older source engine has lots of potential for some juicy bugs. So we also started this work a bit more than a year ago as a pandemic project while we were all at home. There was also a public leak of the source code on GitHub, which has proven to be very helpful. And we also played it extensively at some point in our lives, and we thought like it would be super cool if we could pwn it. So yeah. So what is our attack scenario? We specifically focused on server-to-client vulnerabilities as the server-side code was already like thoroughly audited, and also it seemed quite robust. Yeah, there are lots of community servers. Everyone can like host one, and even during our testing, players joined our server at random. I think we also crashed someone at some point, and yeah, so this definitely seemed like a realistic attack scenario. And well, yeah, once we have pwned one client, we can also iterate through the player's friends list and just send out crafted Steam invites to make them join our servers and pwn them as well. To give you some background, we first need to cover like the setup and some of the tooling that we built specifically for this project. So the client uses a so-called information concealment engine, like a symmetric block cipher for encryption. They only perform a real key exchange on official servers, and on community servers, the key is always hard-coded and tied to reversion. Because apparently they prefer to write their own like networking protocol on top of UDP for speed improvements, the baseline networking code includes like fragmentation layers and also supports compression. On top of this like adjusted UDP protocol, the main method of communication is via protobufs, where they exchange like messages of various types, which are either bidirectional, only from client to server, or only from server to client. We explicitly target these messages and we'll be making references to them throughout the talk. So we built a proxy that allows us to inspect, dump, drop, or even modify these messages in real time. And it has been super helpful for analysis, testing the vulnerabilities, and subsequent development of exploits. So here's like a short demo of the proxy in action. On the left-hand side, you can see the player moving, shooting, changing weapons. And on the right-hand side, you can see the messages that are being like, yeah, that we capture in real time, basically. Yeah, so the source engine was released way back in 2004, and is mostly written in C++. So this already sounds super promising. As security back in 2004 was quite different to like modern security practices. So most prominently, there was like a classic stack buffer overflow in the parsing of encryption parameters, and it has been since fixed. But since Counter-Strike is also compiled without stack cookies, it makes exploiting these kinds of vulnerabilities rather easy, especially in the past. There are various lines of codes that do not seem to be actually used in the game. The whole architecture of the game is quite complex, and it's definitely not immediately clear what code is responsible for what. The developers also use lots of asserts, which they sometimes use for balance checking. Fortunately for us, those asserts do not actually end up in the release build. So this made finding some of the out-of-bounds accesses very easy. So lesson learned, do not use asserts for bounds checking. If they are definitely not, if they're compiled into release builds, not compiled into release builds. So now I'm going to hand over to Simon. He will talk about the first bug, the info leak.
Okay, thank you, Carl. So, you know, although there were some decking mitigations, we still needed to break ASLR, which is why we started looking for an info leak. And to start explaining this bug, I want to give you some background, just to have some context in order to understand the info leak. So CSGO has a problem, which is that anyone can host a community server with maps that are not typically shipped with CSGO by default. Those are your surf maps or hide and seek or whatever you want to play. And they might ship with some game assets that the client does not have. Now, this is a problem, as every time the CSGO server changes the map, all players that don't have the map downloaded would get disconnected. And as you can imagine, that could be quite frustrating if you get disconnected like every 10 minutes. The solution to this problem is to enable players to dynamically download maps at the beginning of each round. The way this works is that the server sends the client a HTTP URL during the connection stage from which to download files from. And we actually discovered a path traversal bug in the download functionality, but it turned out to be a duplicate, which is unfortunate. But we further investigated and found an interesting parser differential bug that led to a powerful info leak. So with the next slides, we'll break down the high-level logic flow of the download functionality as it was implemented on Linux. CSGO also works on Linux, which is cool, and we prefer working on Linux as we're more familiar with it than Windows. And I will come back as to why that is important in a couple of slides. So at the beginning of each match, the server sends the client a list of files that are required to play during the current match, whether that is sounds or skins or any other game asset you could think of. And the client then simply concatenates the missing file name with the HTTP URL they received during the connection stage. The download is implemented using libcurl on Linux. Now let's look at some reverse code and interesting behavior. When CSGO set up the curl request, it registered a callback that is called for each header in the HTTP response. This is the curl header callback you can see here, and it basically just receives a pointer to the header, and that's it. And then there's also a curl write callback, which is called when the HTTP body is received, which contains a pointer to the buffer containing the body. Now looking at the code of the curl header callback, we can see that there's a case-sensitive compare against the header name, and if it equals content length, a branch is entered. And we'll discuss what happens inside of that special branch on the next slides. So we have just seen that the content length header is processed and interpreted by CSGO. The value of it, which is an integer, is used by CSGO to allocate a buffer that is large enough to fit in the HTTP response body as given by the HTTP server. The buffer is then written to disk with the desired file name via the curl write callback. So now for the parser differential. On Linux, the CSGO client parses the header case sensitive, but the underlying library, which is curl, case insensitive. This naturally leads to confusion between the two. If we now tell CSGO, the CSGO client, to create a large buffer on the heap by setting the content length header to an arbitrary value, but then just not send a body or an empty body, the CSGO client will happily write uninitialized memory to disk. So to illustrate this point a bit more, here's an example HTTP response sent by a malicious server. So as can be seen, two content length headers are present in response. And the first time it occurs, it uses capital letters and has the value 1337. And the second time it occurs with lowercase letters and has the value 0. So CSGO only recognizes the first header and allocates a buffer of size 1337. Curl, on the other hand, expects an empty body now that it recognized the second header and uses it as the value, and then proceeds to write the buffer to disk, and it does return an error. And this file will now contain uninitialized memory. That is because the curl write callback is never actually called because the body is empty. So now to Windows. On Windows, they use an entirely different HTTP library, and they actually used completely different code, but the same proof of concept that I just showed you, actually worked on Windows without having to be modified, which was kind of cool. And so on Windows, instead of curl, they used the built-in Windows Internet API, and they used a couple of functions. So first, they would open a client resource with Internet Open, and then they would open specifically HTTP resource with Internet Open URL. And then they use that resource to make the HTTP request with Internet read file. And then some interesting things happened where they used HTTP query info on the resource to gather some information about the request. For example, you could request the values of some headers. And in this case, they used HTTP query info to retrieve the value of the content length header, similarly to the implementation in Linux. Now, what was interesting is that Windows didn't complain when we retrieved that value. And actually, the real size of the body is returned by Internet read file instead of HTTP query info. So again, they did not compare the values and use the wrong value without a body ever being received and written to the body buffer and wrote that file to disk. So in order to break ASLR, we can now spray the heap with objects that contain function pointers and then deallocate them again. And luckily, the CSGO process did not clear allocated memory when it was allocated or freed. This means that the buffers that were written to disk would contain anything that was written to the memory beforehand and then freed again. So you have to keep in mind, though, now we have files on the client of arbitrary size, that contain uninitialized memory, including some juicy pointers. But they're stored on the client's disk. So now we had to find a way to retrieve those contents from the client's disk. And we thought, okay, maybe we'll have to find some super sophisticated side channel leak or any way to leak the files. But as it turned out, it was very easy because, funny enough, the CSGO server can just ask the client to upload any file that is in the CSGO directory. We assume this was done to verify some files on the client, and instead of uploading a hash of the file or CRC or whatever, they would just upload the entire file. This meant we could just parse the file, look for some pointers that we were looking for, which contained some function pointers to the base image, and we broke ASLR. And the info leak was 100% reliable. We tested it many times, and it almost worked every single time on the first try. And even if it didn't work on the first try, you could just retry it an infinite amount of times because you didn't actually corrupt the client's memory, and you could just ask them to re-download the files again and repeat the whole process. So now that we had a reliable info leak, we were ready to corrupt some memory, which is what Niklas will be talking about next.
Yes, thank you, Simon, for the info leak. So obviously, we also need some way to corrupt memory. And it is to say why we tried the following methods to find bugs on both server and the client side. We were only able to find bugs on the client side. The server side has already been pretty hardened since source leak in 2020, sorry, and didn't yield us with any bug whatsoever. So to get a feel for the networking attack surface, we utilized our networking proxy and started to modify with some of the protobuf messages and played around the values a bit. So, and this showed promising results as we are able to find quite a few issues. Sadly, however, the majority of bugs were simple null pointer derefs, and which is not in our interest as we were hoping for an RCE, and crashing the client is not really a security concern, at least not for us. However, in the end, we found quite a neat out-of-bounds access bug, and yeah. So additionally, we also used knowledge that asserts were not compiled into the release build and manually audited the source, and that also yielded us with an interesting bug. So one of the out-of-bounds access was in split screen control. To give you some context, the source engine is able to have a two-player split screen session, which can be requested by the client. And the bug is triggered by the split screen control message sent back by the server, and you can see that on the left-hand side. This is to acknowledge the split screen request from the client, and the client uses this message to set up the split screen session and some metadata around it. However, no check on the client is performed if the client has actually requested a split screen session in the first place. So the attacking server is able to send that control message at any time, and the client will happily comply and set up the thingy. So on the right-hand side, you can see an image of the vulnerable code, and the end slot is basically the slot index in the protobuf message, which is unmodified and unchecked whatsoever. Right, so the array we can perform this out of bounds on actualizing the data section, so we have to keep that in mind when we develop the exploit. And also you can see a few lines down the code that virtual call is performed, so we have PC control almost instantly. So to take advantage of this issue, we first need to find a way to place a pointer to controlled memory inside the data section. And luckily for us, the source engine provides us with just the right primitive, and that's CVARs. CVARs, or configuration values for short, are fixed named config values which are part of the bidirectional protocol. For those of you who played CSGO, like setting your crosshair or view model, that's also a CVAR. And they can hold all kinds of types, such as strings or floating points or collars, which are actually interpreted as integers, which is important for later. And the server has actually the ability to set and read CVARs to its liking. So because only a fixed number of predefined CVARs actually exist, they are also stored in the data section, and this is exactly what we need. So in case the CVAR is a string, a pointer will be placed which points to the heap. And the best part is that thanks to the way values are updated, the server has the ability to write null bytes into those strings as well. So the client will only reallocate the buffer if the updated string is bigger or it wasn't a string before. So by repeatedly sending the payload in shrinking chunks, splitting at every null byte, we were able to place any memory we wanted into the heap word server. And that's actually really important because sometimes due to ASLR, it could be that the base image was placed at the section where null byte was in the pointer, and then the whole exploit wouldn't work. So, and we additionally used another trick with CVARs, and that has to do with the color attribute. And we needed that to place a control pointer. Like with the string, we can only control the contents, but not the pointer, but we also needed the pointer. So, but contrary to pointers, the integer values are first obscured before they are stored. You can see that in the screenshots on the right. And a comment in the source engine actually tells us that this was to make it harder to find the value in memory using cheat engine. And that could have proved a tough roadblock for us actually, because we had no way to predict the encoding. However, thankfully, the encoding was done via the dis pointer, and because we leaked the base image with the info leak already, we can predict the encoding and so still place any value we wanted into the memory. So if they used a random value, that wouldn't have worked. So let's have a quick overview over the game plan. So the first error is the out of bounds access of the split screen array, and this will point to the fake string, the CVAR string object, which will point to our fake object on the heap. So now we have to create a valid virtual table for the virtual call to take PC control. And we use the second CVAR to write a single jump gadget and point it to the, so we pointed the virtual table to the second CVAR we used as with the color object to point it to a single jump gadget inside the main text section. And then we just pivoted into a ROP chain, and I will talk about that now. So thanks to the nature of virtual calls, we have at least some context to play with, or some registers. In this case, the dis pointer is stored in ECX, and because our fake object is entirely controlled, we have a pointer to memory we have chosen beforehand to our advantage. And actually, while we were developing the exploit, while multiple updates were released to the game, which is quite rare, so we were quite unlucky, and sometimes gadgets were added or removed. So in a few cases, EBX also pointed to the fake object, and that simplified the jump chain quite a bit. So in both cases, we pivoted the stack to the fake object, as this controls a good chunk of memory suitable to holding a ROP. So in the first one, we first need to exchange ECX with EAX, and then do the pivot after an additional jump gadget. And in the second one, we were able to pivot immediately. So, and for the ROP chain, we just used the generic ROP to system or shell execute A, depending on the OS, which is enough to give us control over the client. So let's have a quick demo.
Yeah, let's maybe watch it a second time. Yeah. So what is the actual impact of this bug? Well, we can reliably execute code on the victim's machine. So the info leak can be performed multiple times until we are certain that we have all the pointers that we need. And the out of bounds issue is, and the memory corruption are also reliable, assuming the info leak is valid. So from here on, attackers could easily steal private information, stage malware, steal expensive keys, or install crypto miners. It would also just be as easy to send out more Steam invites to pawn even more people, or just use the PC as part of the botnet. So one more thing. Let's also talk about the disclosure timeline. So we have reported the bug through HackerOne on the 4th of January last year, and it was actually tried a couple of days later by a HackerOne employee, and then nothing happened for almost 3 months. So yeah. We already gave up on getting a bounty, and we hope to just get a blog post at some point. But then some other people actually published posts about Counter-Strike vulnerabilities on Twitter, and we joined them and published a video of our exploit as well. And then, after a couple of days, a couple of news outlets actually covered the vulnerabilities, which then apparently made Valve focus on the HackerOne reports, and we noticed that they were slowly getting fixed, and that gave us hope. Eventually our report was fixed, and we actually received $15,000 as a bounty. Yeah, but unfortunately, the communication was only through a HackerOne representative, and we never got any message from a Valve employee. Yeah, so this is the end of our talk. Feel free to ask us any questions. You can also reach us through Twitter. And yeah, that's it.